Okay, good morning, Physics 30. Alrighty, so this is my second try at recording this because I made a mistake and didn't record my voice last time. Alrighty, so we are on to lesson 3 here. Okay, hopefully you've summarized the 3 hand rules for yourself here. Alright, remember we're going to use left hand for negative and right hand for positive. Okay, it's going to be very important as we get into the third hand rule especially, okay? Oh, sorry, a little too far. So the first thing we're going to do is we're going to talk about how we find the magnitude of the force on a moving charged particle, okay? Has to be a charged particle, all right? Has to be a charged particle, and it has to be moving, okay? That's critical because you'll notice in this equation that there is a V. In this equation, since there is a V or velocity, if it's not moving, then this whole equation gets canceled out and equals 0. All right. The next thing I want you to notice in this equation is that there's this little symbol there, that kind of upside down T. That is a perpendicular symbol. What that means is that the velocity must be perpendicular to the magnetic field. All right. The magnetic field is capital B. I don't know why off the top of my head. Okay. But it is measured in Teslas. So it's capital B measured in Teslas, which is after Nikola Tesla. All right. Force, magnetic force is of course measured in newtons. Q measured in coulombs, and velocity measured in meters per second, and make sure you double check those all the time. All right. Note that again, like the direction of travel has to be perpendicular. If it is not perpendicular, you have to find the perpendicular component. Okay, perpendicular component means you can break into the x and y's. All right. So if I look over here, I have 3 identical charges. Okay, enter a magnetic field at the same time as shown in the diagram. Identify the particle that would experience the greatest magnetic force. Explain your choice. So we'll start with A here. Okay, if you look at A, what you'll notice is that it is not going perfectly perpendicular. It is some perpendicular, but some is going parallel. So we'd only worry about the perpendicular component, right, which is going to be less than if it was straight perpendicular. Then we look at B here. B is actually perfectly parallel, so it actually have a force of 0, so that can't be the answer, right? C is perfectly parallel, so therefore it is going to automatically be the strongest force since it's perfectly parallel, right? So, or perpendicular, sorry. Okay, so this would be, B would be 0, A would be some, and C would be the most. So C would have the greatest magnetic force. All right, Nikola Tesla, there's a few things about him. He's basically the father of electricity is what he's kind of known for. He says that some of his ideas were stolen. There's a whole bunch of controversy about him as a scientist, right? But keep in mind that people obviously revered him. Einstein did once say how it felt to be the smartest man alive, and he said, I don't know, you'll have to ask Nikola Tesla. Very smart, very rich, very well educated, and very good at what he did. Okay, so of course, when you're good at stuff, you get to name things, okay, like the magnetic field force. One thing to keep in mind is don't believe everything you read, right? Because, for example, this could just put this up. It looks real believable until you realize that it's Abraham Lincoln talking about the internet. It doesn't make sense. Alrighty, so this equation here is down here. Okay, this is our force equals QVB. What you'll notice is that both the B and the force have those bars on the outside. That means the direction is not going to be told to you. All right, so that's particularly important for the force, right? For the force, right, since it has these bars on the outside, it means that the equation won't tell you the direction. What does tell you the direction is the hand rules. We have to use the hand rules to tell direction. I'm still learning how to write here, guys. It's not too bad. We have to use the hand rules to tell direction, all right? Okay, and for B, the reason it has its little bars around it, right, if I look at B there, is because as long as it's perpendicular to velocity, it doesn't matter which direction it's going, okay? Alrighty, so for this one here, we have kind of this idea where we always talk about units, okay? Teslas is what we measure B in. If you do this equation here, right, if you follow this, okay, check that out. See if you follow along what happened there, right? First we isolated for B, then we say what it's equal to, and then we put in the units, right? Force is measured in newtons, QV is coulombs meter second. We did the upside down flippy thing for the meter second, and we get newton seconds per coulomb meter. Again, do not memorize this. You're not required to in this course, but you are required to understand how this is done. Make sure you understand how that's done. If you don't, please ask me questions, okay? All right. When we're talking about magnetic fields, when when we're talking about magnetic fields, okay, there's some things to kind of make it relative to you what a Tesla is and how large it is, right? So, for example, the Earth's magnetic field, which is strong enough to move a compass and deflect some charged particles from hitting us, is about 0.0005, right? Or it would be, let's see here, 0.5, yeah, about 0.05 milliteslas, right? So it's not very large. A bar magnet, right, you can pick up paper clips and a few things like that. It's about a 0.01, okay? Then we get into the low field MRI, right? So these are the medical machines. MRIs are basically based off magnets, all right, that do a lot of funny things to particles in your body, which is pretty cool how they work. It's going to be about 0.2, so about 20 times the strength of a bar magnet. Then you have a high field MRI, which is going to be 150 times the strength of a bar magnet, right? Humans have been trying to make magnets. The strongest we've ever made is about 60 Tesla. Okay, that's very strong, right? That's going to be able to do a lot of things, okay? Things that can lift cars and stuff like that are in this 0.2 to 1.5, those electromagnets. All right, a neutron star, if you got some time, Google what a neutron star is. It's basically a large star that's been packed down into a very small amount by gravity. Okay, it's spinning and it's got charged particles, but not charged particles because they're neutrons. But anyways, it is got a magnetic field of approximately that's in the trillions, it looks like. Okay, that's very large, right? So again, key in on these two here, Earth and the low field MRI, the bar magnet, just to give you a concept of approximately how big we're going to have these kind of ideas, okay? So one other thing that we're going to introduce here is something called a positron, all right? The positron is the antiparticle of an electron, all right? So an electron is a negative, very, very small, okay? It has what's called the antiparticle, meaning a positron. So every particle actually has an antiparticle. Sorry. Has an antiparticle. When a particle and its antiparticle meet, they actually destroy each other. These are very rare. These are very common. Okay, a positron is not something you deal with a lot, but the cool thing about it is it exists to begin with, and it has the exact same mass and exact same charge as an electron, but it is positive rather than negative, right? Pretty creative that they said that a positron is a negative electron. It makes sense, okay? It's also on the back of their formula sheet. You'll actually see it if you look in kind of on the right-hand side, halfway down, you'll find positron. All right, so we have a question here. A beam of positrons traveling north at 4 times 10 to the 5 meter second enters an upward magnetic field of 30 millitesla that's perpendicular to the direction of the beam. To determine the initial direction of the magnetic force. Okay, so we have to first determine the initial direction, right? And as soon as we ask for direction, this equation doesn't give us direction, right? We can't use that. We do have to use our right hand, right? Okay, so why are we using our right hand instead of our left? Well, the answer is because it's positive. Positive means right hand. All right, so this is a charged particle moving through a magnetic field, which means it's our third rule, right? Our third rule, we go back and we can look. You guys should have it written here, right? But I can go back and look here, right? So our fingers are the flow of whatever's moving, the charged particle. Sorry, thumb is in the charged particle direction, fingers are the magnetic field, and the palm is the magnetic force, okay? So we go back here, let's read through this question one more time. So a beam of positrons traveling north is at this. Okay, so it's traveling north, right? So on our kind of paper, north is to the top of the paper. So our thumb should be pointing to the top of the paper. Then it says enters an upward magnetic field. So that means that upward means away from the paper, right? So it's going to be that kind of dot look, right? Okay, so it's going to be upward. So your thumb should be pointing to the top of the paper and your fingers pointing to the sky. Okay, what that means using our right hand is that the magnetic force should be to the right, okay, to the right or to the east, right? Since they've used the word north, we're going to just follow suit there and say to the east. All right, to the east. I promise my writing will get better. I've got to get a better stylus, and I'm going to do that today. All right, so I've already written out this. So we're going to act for the magnitude of the force, right? So the magnitude of the force, we're going to use the equation, okay? And the equation here is F equals QVB. Again, you can put the bars and the lines if you want, but you guys know that you can kind of understand that to begin with. All right, so we're going to use that equation. I've already written out the variables, right? We know that the charge, okay, the charge here is 1.6 times 10 to the negative 19 because it has the same charge as an electron but is negative, or is positive, sorry. So it's 1.6 to 10 19. The velocity is 4 times 10 to the 5. That came from here. And the magnetic field is 30 milliteslas, which is times 10 to the negative 3. So if you look on the back of the formula sheet, you'll notice that I've replaced the m with times 10 to the negative 3 because our formula sheet tells us that m means times 10 to the negative 3. We go ahead and you can punch that onto your calculator, right? And punch it on your calculator. Again, it's this force magnetic. Okay, so you're going to type it in 1.6 to the negative 19 times 4 to the 5 times 30 to the negative 3, and you're going to get the number of 1.92 times 10 to the negative 15. All right, that is going to be measured in newtons, and the direction, of course, we already figured out is to the east in this case. All right, so you have 1.92 times 10 to the negative 15 newtons, and that's kind of the way it works. All right, this is where normally you guys should ask a question. You probably wouldn't, but you might ask the question, well, that seems like a really small force, which it is, right? It's a very small force, times 10 to the negative 15, right? But what we should also say is that since it's a positron, which has a very small mass, right? The mass of an electron or a positron is 9.11 times 10 to the negative 31. This small force is gonna create a huge acceleration on these very small particles. Okay, so just kind of keep that in mind, that you're usually dealing with small numbers when you're dealing with force in this case, all right? And just kind of keep that as a part of it, all right? Okay, so that is the end of lesson 3. We are now going to do practice problems 6 to 10. Okay, I promise you guys should be able to figure this all out. Hopefully these videos are helping. Let me know. Okay, if you need to do your next chunk of your anticipation guide, or if you have a velocity sector, I'm gonna release the next video either today or Monday morning to you guys, so you can kind of keep trudging through. All right, remember, send me questions through email or through Google Classroom. Also, please be prepared to contact me during our Google Hangout, which I believe is either Wednesday or Thursday, but you'll get a note about that coming out. All right, check your emails, and good luck, guys.